October 15th, 1944, Wright Field, Dayton, Ohio. Oberleutnant Hans Fay, Luftwaffe technical intelligence officer and experienced jet pilot, stood with his arms crossed as American engineers wheeled out what they claimed was their first operational jet fighter. The German officer's expression shifted from professional interest to barely concealed amusement. "Your jet has a propeller," he observed, pointing to the aircraft's nose. The Americans exchanged uncomfortable glances. "That's the P-59 Era Comet," explained Colonel Marcus Cooper of the Army Air Force's Material Command. "It's transitional. Our real jet fighter is coming." Fay walked slowly around the dumpy aircraft with its underwhelming General Electric I-16 engines mounted in bulbous nacelles. He had flown the Messerschmitt Me 262, an aircraft already in combat service that could exceed 540 miles per hour. This American machine looked like it might struggle to catch a Spitfire. "Gentlemen," Fay said with diplomatic restraint that barely masked his skepticism, "Germany flew its first jet aircraft in 1939. We have been mass-producing operational jet fighters for months. You're showing me something that appears to belong in a museum of failures. When will America have a real jet?" The answer would come sooner than any German could imagine, and it would render their early advantage meaningless. Within months, a revolutionary aircraft designed and built in just 143 days would demonstrate that American engineering, when properly motivated and freed from bureaucratic constraints, could achieve the impossible. The Lockheed P-80 Shooting Star would become the jet fighter that defined the future, proving that German engineers had been laughing at the wrong things. This is the story of how a secret project in a circus tent transformed American aviation, how one aircraft erased Germany's years of jet development advantage, and how the engineers who mocked American jet efforts would be studying captured P-80s with expressions very different from amusement. The humiliation Hans Fay witnessed at Wright Field was real and justified. The Bell P-59 Era Comet, America's first jet aircraft, was an embarrassment. Underpowered, sluggish, and unreliable, it was slower than the propeller-driven P-51 Mustang in level flight and handled like a truck with square wheels. The project had begun with such promise in September 1941 when the British, already developing Frank Whittle's pioneering jet engine, offered to share their revolutionary technology with the Americans. The Air Corps selected Bell Aircraft to develop America's first jet fighter, reasoning that Bell's experience with unconventional designs, like the P-39 Era Cobra, made them ideal candidates. What followed was a masterclass in how not to develop revolutionary technology. Bell's engineers, lacking any experience with jet propulsion, made fundamental mistakes. They designed the aircraft around British engines that were already obsolete by the time the prototypes flew. They positioned the engines in the fuselage sides, creating massive drag and leaving no room for fuel. They gave it straight wings, optimized for low-speed handling, completely missing the implications of high-speed flight. The XP-59A first flew on October 1, 1942, at Muroc Dry Lake in California. Test pilot Robert Stanley reported that it flew smoothly, but lacked the performance expected from a jet. That was generous. The truth was that the P-59 was a technological dead end, an aircraft overtaken by events before it entered production. By 1944, when limited production models reached operational test units, pilots were openly derisive. Captain John Myers, assigned to evaluate the P-59 at Muroc, filed a report that circulated widely through Air Force channels. The P-59 Era Comet is underpowered, unstable at high speed, and possesses no advantages over existing propeller fighters. Its maximum speed of 413 miles per hour is barely faster than a P-47 Thunderbolt and significantly slower than the latest German fighters. The aircraft exhibits compressibility problems above 0.78 Mach, making it dangerous to dive. Visibility is poor, range is inadequate, and the engines are unreliable. Recommendation: terminate production immediately and develop a proper jet fighter using lessons learned from this failure. The P-59's failures were America's introduction to jet aviation, and they were watching from behind. The British had been flying jets since 1941. The Germans had operational jet fighters in combat by July 1944. The Soviets were developing their own jets based on captured German technology. America, the nation that had built over 100,000 aircraft in 1944 alone, couldn't build one decent jet fighter. This technological humiliation burned in the minds of American aviation leaders. General Henry Hap Arnold, commanding general of the Army Air Forces, was particularly frustrated. He had visited Britain in April 1944 and seen the Gloucester Meteor, a genuinely capable jet fighter entering RAF service. He knew from intelligence reports that German jets were appearing over Europe with increasing frequency. Arnold understood that whoever mastered jet technology would dominate post-war aviation. He couldn't accept that America would be left behind. The solution would come from an unlikely source, a secretive aircraft company known for building some of the war's strangest airplanes, and a legendary engineer who thrived on impossible deadlines. Clarence Leonard Kelly Johnson was already a legend in aviation circles by 1943. The brilliant young engineer had joined Lockheed in 1933, fresh from the University of Michigan, and immediately began revolutionizing aircraft design. He had designed the Lockheed Electra's distinctive twin tail, created the P-38 Lightning fighter, and was known throughout the industry for his unconventional solutions to difficult problems. But Kelly Johnson had a reputation for more than engineering genius. He was notoriously difficult, demanding, and intolerant of bureaucracy. He believed that small teams of talented people working with minimal oversight could achieve more than large organizations burdened with committees and paperwork. He had proven this repeatedly with his projects at Lockheed, but the conservative military acquisition system frustrated him constantly. In June 1943, Johnson had proposed creating a separate development unit within Lockheed that would operate independently from normal company procedures. He wanted a team that could design and build experimental aircraft with unprecedented speed, free from the meetings, reports and interference that slowed conventional projects. Lockheed management, initially skeptical, agreed to let Johnson try his approach on a small project. They gave him a corner of the Burbank plant, a handful of engineers, and instructions to stay out of everyone else's way. Johnson called his operation the Skunk Works, a name borrowed from the Moonshine factory in the Lil Abner comic strip. The original team consisted of 23 engineers and 105 shop workers. They worked in a rented circus tent next to a plastics factory that produced such noxious odours that workers joked they were operating downwind from the actual skunk works. The conditions were terrible, the hours brutal, and the bureaucracy non-existent. Kelly Johnson's engineers loved it. Their first project, the P-80, would prove that Johnson's methods could achieve the impossible. The telegram arrived at Lockheed on June 17, 1944. General Arnold wanted to meet with Johnson immediately regarding an urgent jet fighter requirement. Johnson flew to Washington the next day and was ushered into Arnold's office, along with several other generals and technical officers. Arnold got straight to the point. The Germans have operational jet fighters in combat. The British have jets in service. We have the P-59, which is garbage. I need a real American jet fighter, and I need it fast. How quickly can Lockheed deliver? Johnson, never one to undersell his abilities, asked about the specific requirements. Arnold handed him a thick document outlining performance specifications, armament, range, and dozens of other parameters. Johnson flipped through it for less than 5 minutes before responding. General, with respect, these requirements are written by people who don't understand jets. Half of these specifications contradict each other. The other half are impossible with current technology. Give me the essential requirements and let me design a proper jet fighter. The room went silent. Officers didn't typically tell generals that their requirements were nonsense. Arnold, to his credit, recognized that Johnson was exactly the kind of engineer he needed. What do you need? Speed above 500 miles per hour, Johnson said immediately. Combat radius of at least 400 miles. 650 caliber machine guns or equivalent armament. Service ceiling above 40,000 feet. And it has to be reliable enough for average pilots to fly, not just test pilots. Arnold nodded. How long to build a prototype? Johnson performed calculations on a notepad for several minutes. The room remained silent as he worked, occasionally crossing out numbers and starting over. Finally he looked up. 180 days from contract signature to first flight. The officers exchanged skeptical glances. The P-59 had taken over a year from contract to first flight, and that was using British engines and extensive technical assistance. Johnson was proposing to design an entirely new aircraft from scratch in half that time. General Frank Carroll, chief of the engineering division, spoke up. Mr. Johnson, with all due respect, that's impossible. We'd need to approve drawings, review designs, inspect manufacturing processes, conduct ground tests. The procurement process alone takes longer than 180 days. Johnson's response would become legendary in aviation history. Then change your procurement process. Give me a contract, give me access to whatever engines you want me to use, and stay out of my way. I'll give you a jet fighter that will make the Germans rethink their advantage. I don't need oversight. I need freedom to work. Arnold smiled. It was the kind of audacious confidence he needed. You have 180 days, Mr. Johnson. Don't make me regret this. The contract was signed on June 23, 1944. Johnson's team actually got the aircraft flying in 143 days, 37 days ahead of schedule. But first, they had to design something that would work. Kelly Johnson's approach to aircraft design was fundamentally different from conventional methods. While most companies assembled large teams that worked on separate components before integrating them, Johnson believed in small teams that understood the entire aircraft. He wanted every engineer to see how their decisions affected the whole machine. The first design meeting for what would become the P-80 took place in late June 1944 in the Skunk Works tent. Johnson assembled his core team, 18 engineers who would be responsible for every aspect of the aircraft. He began by listing what they knew about jet aircraft design from studying intelligence reports on German jets and British technical data. Jets produce tremendous thrust but consume fuel at staggering rates. High-speed flight generates compressibility effects that straight wings can't handle efficiently. Engine reliability is the critical weakness of all current jets. Visibility is essential since jets fight at altitudes where visual acquisition is difficult. The fuselage must be designed around the engine, not the other way around. Johnson drew a simple side view profile on a blackboard. Thin fuselage, barely larger than the engine itself. Straight wings for simplicity and ease of manufacture, but thin and positioned low to minimize interference drag. Tricycle landing gear for better ground handling and pilot visibility. Flush riveting throughout to minimize drag. Simplicity above all else. W.P. Ralston, Johnson's chief project engineer, pointed at the drawing. Kelly, that's going to be cramped. The pilot will be sitting practically on top of the engine. Johnson nodded. Good. Shorter fuselage means less weight, less drag, better performance. The pilot doesn't need a living room, he needs a fighter that works. What about the engine? Asked Art Vierek, the propulsion specialist. We're stuck with whatever the army gives us. Johnson had already investigated this critical question. The British Halford H-1 engine was available, the same power plant used in the de Havilland Vampire fighter. It produced 2,460 pounds of thrust, far more than the anemic engines in the P-59. The Army Air Forces had secured rights to build the engine under license as the Allison J-33. It's reliable, Johnson explained. The British have been flying it for months without major problems. It's not the most powerful engine available, but it's proven. We'll design the aircraft to be efficient enough that 2,460 pounds will be adequate. The team worked 18-hour days, 7 days a week. Johnson established rules that would later become famous as Kelly's 14 Rules of the Skunk Works. Small teams, minimal reporting requirements, direct communication between engineers and shop workers, authority delegated to the lowest possible level, and most importantly, complete freedom from outside interference. By mid-July, the basic design was frozen. The P-80 would be a single-seat, single-engine jet fighter with straight wings, a streamlined fuselage, and conventional tail surfaces. It would weigh approximately 8,000 pounds empty and carry 425 gallons of fuel in fuselage tanks. Armament would be 650 caliber machine guns in the nose with 300 rounds per gun. The simplicity was deceptive. Every component was optimized for weight and efficiency. The wing used a thin laminar flow airfoil that reduced drag significantly. The fuselage was constructed using techniques borrowed from racing aircraft, with flush riveting and careful attention to surface smoothness. The engine installation used a straight-through air path, minimizing pressure losses that robbed thrust. While Johnson's team designed, the shop workers began building. This was unconventional. Normally, designs were completely finished before manufacturing began. Johnson wanted components being built while engineers were still refining other parts of the aircraft. It was risky, requiring constant communication between design and manufacturing, but it saved enormous amounts of time. The fuselage took shape first, built upside down on a special jig that allowed workers access to the internal structure. The skin panels were hand-formed over wooden molds, each piece checked repeatedly for proper contour. The wings were built simultaneously in another section of the tent, with stringers and ribs assembled around the main spar. By September 1944, just 3 months after the project began, the XP-80 was recognizable as an aircraft. The silver fuselage gleamed under the tense work lights. The wings were mated to the fuselage, and the tail surfaces were being attached. Lockheed workers, accustomed to building aircraft on assembly lines with thousands of identical components, marvelled at the handcrafted fighter taking shape in the tent. "This ain't mass production," observed one veteran riveter. "This is custom work like building a hot rod." That's exactly what it was. The XP-80 incorporated refinements impossible in mass-produced aircraft. Every fastener was carefully selected, every joint was precisely fitted, every surface was smoothed and polished. Johnson was building a race car that happened to fly. The engine arrived from Britain in late September, carefully packed and accompanied by British engineers who would assist with installation. The Halford H-1, soon to be designated the Allison J-33, was a centrifugal flow turbojet that looked more like a mechanical sculpture than a propulsion system. At its heart, a single-stage centrifugal compressor spun at 10,000 revolutions per minute, drawing in air and compressing it before feeding it to 10 combustion chambers arranged around the engine's circumference. Installing it was like solving a three-dimensional puzzle. The engine had to fit precisely in the fuselage, positioned so its centre of thrust aligned with the aircraft's centre of gravity. Fuel lines, electrical connections and control cables had to be routed around it. Air had to flow smoothly from the intake in the nose through the engine and out the tailpipe without creating turbulence or pressure losses. Johnson personally supervised the installation, often climbing into the fuselage to check clearances and routing. British engineer Frank Whittle, the brilliant inventor who had pioneered jet engines, visited the Skunk works in October and watched Johnson work. Whittle was impressed by the Americans' attention to detail and understanding of jet propulsion principles. "You're building this like a racing motorcycle," Whittle observed. "Every component optimized, every ounce of weight questioned." Johnson grinned. "That's exactly right. We're not building a weapons platform that happens to fly, we're building a flying machine that happens to carry weapons. There's a difference." By early November 1944, the XP-80 was complete. It had taken 143 days from contract signature to roll out, an achievement unprecedented in aviation history. The aircraft was disassembled, loaded onto trucks, and transported to Muroc Dry Lake in California's Mojave Desert, far from prying eyes and close to the vast empty spaces needed for flight testing. Reassembly at Muroc took 3 days. On November 15th, the XP-80 sat on the dry lake bed, fueled and ready for its first flight. Milo Burcham, Lockheed's chief test pilot, performed his pre-flight inspection with Johnson hovering nearby like an anxious parent. Burcham was a veteran test pilot with thousands of hours in everything from racing planes to heavy bombers. He had test-flown the P-38 Lightning and knew Kelly Johnson's designs intimately. But this was different. This was America's bid to join the jet age. The startup procedure was exotic compared to propeller aircraft. Instead of the cough and roar of a piston engine coming to life, the jet engine spooled up with a rising whine that built to a steady howl. Burcham advanced the throttle carefully, feeling the aircraft surge forward with smooth linear acceleration, unlike any propeller fighter. He taxied to the end of the lake bed, turned into the wind and performed final checks. Johnson watched through binoculars from the flight line, surrounded by his engineering team. Everyone was silent. 143 days of brutal work, thousands of hours of calculations and fabrication came down to the next few minutes. Burcham advanced the throttle to full power. The jet engine's howl became a scream. The XP-80 accelerated smoothly, the tricycle landing gear keeping the fuselage level. At 90 miles per hour, Burcham eased back on the stick and the aircraft lifted off, climbing into the California sky with surprising eagerness. For the next 45 minutes, Burcham explored the aircraft's characteristics. He climbed to 20,000 feet, noting the effortless acceleration that no propeller fighter could match. He performed gentle turns, discovering that the controls were responsive but required more force than conventional fighters. He reduced power and extended the landing gear, checking handling qualities at low speed. Most importantly, he pushed the throttle forward and accelerated, watching the airspeed indicator climb past 400 miles per hour, then 450, then 500. The aircraft remained stable and controllable, with none of the compressibility problems that plagued the P-59. When Burcham landed and shut down the engine, He climbed out of the cockpit with a broad smile. "Kelly," he said, "you've built something special. That airplane feels 10 years ahead of anything else flying." Johnson's relief was visible. He had delivered on his promise to General Arnold. The XP-80 worked, but working was just the beginning. The aircraft needed to prove it could outperform German jets and be manufactured in quantity. The flight test program proceeded at a pace that shocked conventional test organizations. Kelly Johnson believed in aggressive testing, pushing aircraft to their limits quickly to identify problems early. Within a week, the XP-80 had flown 20 test flights, exploring the entire performance envelope. The results exceeded expectations. Maximum speed at optimum altitude approached 580 miles per hour, significantly faster than the Messerschmitt Me 62's 540 miles per hour. Rate of climb was exceptional, reaching 20,000 feet in under 5 minutes. Service ceiling exceeded 45,000 feet, higher than any operational fighter. Most impressively, the aircraft was stable and predictable throughout its flight envelope, with none of the nasty surprises that had plagued other early jets. But there were problems. The engine flamed out unpredictably, during certain maneuvers, particularly in rapid throttle changes. The fuel system sometimes starved the engine during negative G maneuvers. The cockpit became uncomfortably hot from engine heat, radiating through the fuselage walls. And tragically, on March 20th, 1945, Milo Burcham died when his engine failed during a high-speed test flight, and he couldn't escape before the aircraft crashed. Johnson was devastated by Burcham's death, but he understood that pushing the boundaries of flight technology was inherently dangerous. The accident investigation revealed that a compressor blade had failed due to metal fatigue, a problem that could be solved with improved materials and manufacturing processes. The test program continued with Tony Levier, another experienced Lockheed test pilot, taking over as chief test pilot. By spring 1945, the XP-80 had demonstrated that it was not just faster than German jets, but more reliable, easier to fly, and potentially much easier to mass produce. The Air Force was convinced. They placed orders for 5,000 P-80s, envisioning squadrons of shooting stars that would dominate the skies over Japan. But the war ended before large-scale production began, and America's jet fighter would have to prove itself in a different conflict. While Kelly Johnson's team celebrated their achievement, German intelligence was desperately trying to understand what the Americans had developed. Captured documents from late 1944 showed that Germany's Technical Intelligence Service, the Luftwaffe's Technisches Amt, had received reports of a new American jet fighter undergoing testing in California. The reports were initially dismissed as exaggerated. The Germans had convinced themselves that American aviation technology lagged years behind. They had seen the pathetic P-59 and assumed it represented the best America could achieve. This assumption was a catastrophic intelligence failure born from a combination of arrogance and wishful thinking. German engineers had pioneered jet aviation with the Heinkel He-178 in 1939 and had operational jets in combat by 1944. They assumed this head start was insurmountable. That American industry, for all its production capacity, couldn't match German technical sophistication. They were wrong. The first solid intelligence on the P-80 reached Germany in January 1945 through a technical report smuggled out of neutral Sweden, where American diplomatic staff had carelessly discussed the project. The report included performance estimates that German analysts initially flagged as impossible. An American jet fighter with a maximum speed of 580 miles per hour, a service ceiling above 45,000 feet, better reliability than German jets. The analysts assumed the numbers were inflated for propaganda purposes. Oberst Dietrich Peltz, inspector of day fighters for the Luftwaffe, reviewed the intelligence report and dismissed it with a handwritten note that survived the war. The Americans have industrial capacity but lack our technical sophistication. Their so-called jet fighter is undoubtedly inferior to our Me-262 and will never be produced in militarily significant numbers. This jet will not affect the outcome of the war. Peltz was right about one thing. The P-80 would not affect World War II's outcome, but his broader assessment represented the kind of technological hubris that had led Germany to underestimate American capabilities repeatedly throughout the war. By February 1945, more detailed intelligence reached Germany through various channels. Photographs taken by long-range reconnaissance aircraft showed P-80s at Muroc. Reports from agents in America provided additional details about performance and production plans. Most concerning for German analysts was information suggesting that the P-80 had been designed and built in less than 5 months, an impossibly short time frame by German standards, where new aircraft typically required years of development. General der Jagdflieger Adolf Galland, commander of the Luftwaffe's fighter forces, was one of the few senior officers who took the American jet threat seriously. Galland was a realist who understood that Germany's technological advantages were eroding rapidly. He had flown captured Allied aircraft and respected American engineering. When he reviewed the P-80 intelligence reports, his assessment was far more sober than his colleagues. Galland wrote in a classified memo to Hermann Göring dated March 3, 1945, "Intelligence indicates the Americans have developed a jet fighter with performance equal or superior to our Me-262. More concerning is the reported development timeline of less than 6 months. If accurate, this suggests American industry can iterate and improve jet designs at a pace we cannot match. Our advantage in jet technology may be temporary. Recommend immediate effort to obtain detailed technical intelligence on American jet aircraft." Göring, facing the collapse of Germany and increasingly disconnected from reality, dismissed Galland's concerns. The Reichsmarschall scrawled a note on Galland's memo. "Galland worries too much about American technology. They build quantity, we build quality. The Me-262 is sufficient." Göring's dismissal was symptomatic of the delusion that pervaded German leadership in the war's final months. They had convinced themselves that German technical superiority would overcome material disadvantages, that wonder weapons would reverse military defeats, that quality would triumph over quantity. The P-80 represented something they couldn't accept: American industry matching German innovation while maintaining overwhelming production capacity. It shattered their comfortable narrative about technological supremacy. The first opportunity for direct German assessment of the P-80 came in May 1945, after Germany's surrender. Among the thousands of German aviation personnel who surrendered to Allied forces were some of the Luftwaffe's most experienced test pilots and engineers, men who had flown and evaluated virtually every aircraft in the German arsenal. Major General Hugh Nair, Deputy Commanding General of US Strategic Air Forces in Europe, had an idea. He would arrange for top German pilots to fly American aircraft, including the P-80, and provide their professional assessments. The evaluations would be conducted at Melun-Villaroche airfield outside Paris, where the Air Force had assembled a collection of aircraft for testing and evaluation. In late June 1945, several German pilots were transported to Melun-Villaroche. Among them was Oberst Johannes Steinhoff, a highly decorated ace with 176 victories who had flown the Me-262 in combat. Steinhoff had been badly burned when his Me-262 crashed during takeoff in April 1945 and was still recovering, but he insisted on participating in the evaluation program. Also present was Major Hans Guido Mutke, an experienced jet pilot who claimed to have exceeded the speed of sound in a Me-262 during a dive, a claim that remains controversial. The Germans were first shown the P-59 Era Comet. Their reactions ranged from polite disinterest to open contempt. Steinhoff, examining the aircraft's bulbous engine nacelles and straight wings, commented that it appeared to be a training aircraft rather than a combat fighter. When informed it had been America's first operational jet fighter, the Germans' confidence in their technological superiority seemed confirmed. Then they brought out the P-80. The German pilots walked around the aircraft in silence, their expressions shifting from confidence to concern. The shooting star's clean lines, flush riveting, and careful attention to drag reduction were immediately apparent to experienced eyes. The thin wings, streamlined fuselage, and well-integrated engine installation spoke of sophisticated aerodynamic understanding. "This is a proper jet fighter," Steinhoff said quietly in German to Mutka. The Americans learned quickly. Flight demonstrations were arranged. Captain William Council, an experienced P-80 pilot, performed a series of high-speed passes, rolls, and aerobatic maneuvers that showcased the aircraft's capabilities. The German pilots watched intently, noting the smooth handling, responsive controls, and impressive acceleration. Steinhoff was invited to fly the P-80 first. He spent 30 minutes in the cockpit familiarizing himself with the controls and instruments before starting the engine. The flight lasted just over an hour. Steinhoff explored the aircraft methodically, testing handling characteristics, stall behavior, and high-speed performance. When he landed, his assessment was carefully professional but revealing. This aircraft represents a complete understanding of jet fighter design principles. The handling is excellent, controls are responsive, and performance is exceptional. Maximum speed appears to meet or exceed the Me-262. More significantly, visibility is superior, control at low speeds is better, and the single-engine configuration is more reliable than our twin-engine design. The Americans have built an aircraft that improves upon our innovations. Mutka's evaluation after his flight was even more direct. The P-80 is a better fighter than the Me-262. It is faster, more maneuverable, and far easier to fly. Our aircraft required exceptional pilot skill to operate safely. This aircraft could be flown by average pilots. In mass production, that difference is decisive. Other German pilots who flew the P-80 in subsequent days echoed these assessments. The American jet was not just competitive with German jets, it was superior in most meaningful ways. And most troubling for German engineers who reviewed the technical data, it had been designed and built in a fraction of the time German jets required. The evaluations at Melun-Villaroche shattered any remaining German illusions about American technological capabilities. The nation they had dismissed as capable of mass production but not innovation had produced a jet fighter that represented the future of aviation. The P-80 Shooting Star entered operational service with the US Air Force in early 1946, too late for World War II, but in time to become America's first-line jet fighter during the critical early years of the Cold War. Production ramped up rapidly at Lockheed's Burbank plant, where Kelly Johnson's design proved remarkably easy to manufacture. By 1948, over 700 P-80s had been built, equipping fighter squadrons across the United States, Europe, and the Pacific. The aircraft proved reliable and forgiving in operational service. Pilots transitioning from propeller fighters found the P-80 significantly easier to fly than its reputation suggested. The tricycle landing gear made ground handling simple. The controls, while heavier than propeller fighters, were well harmonized and provided good feedback. The single-engine configuration was actually more reliable than twin-engine jets because there was no asymmetric thrust to manage if an engine failed. But the P-80's true test would come in combat. That opportunity arrived on June 25, 1950, when North Korean forces invaded South Korea. The Korean War would pit American jets against Soviet-designed jets in the first large-scale jet versus jet combats in history. The P-80, redesignated F-80 Shooting Star in 1948 when fighter designations changed, would finally prove itself in the crucible Kelly Johnson had designed it for. The 8th Fighter Bomber Wing, equipped with F-8s, was based in Japan when the Korean War began. They flew their first combat missions on June 27, 1950. Just 2 days after the invasion, providing close air support for retreating American and South Korean forces. Lieutenant Robert Wayne flew one of these early missions and described the experience. We came in low over the highway where North Korean tanks were advancing. The F-80 was carrying 2 500-pound bombs and full ammunition for the guns. I pickled the bombs on a tank column and saw at least one direct hit. The tanks scattered. Then I came round for a strafing run with the 650s. The armour-piercing incendiary rounds tore through the light armour on their vehicles. 2 trucks exploded. A tank shed a track and slewed off the road. The F-80 was perfect for this kind of work. Fast enough to avoid ground fire, stable enough for accurate bombing, and those guns could destroy anything we found. The F-80s dominated North Korean forces in the war's early months. North Korea had no jet fighters, only obsolete propeller-driven aircraft that were easy prey for the shooting stars. American pilots racked up kills quickly, establishing air superiority that allowed ground forces to operate without fear of air attack. But in November 1950, everything changed. Chinese forces intervened in the war, bringing with them Soviet-supplied MiG-15 jet fighters flown by Soviet, Chinese, and North Korean pilots. The MiG-15 was a swept-wing jet fighter with performance superior to the straight-wing F-80 in most respects. It was faster at high altitude, could climb quicker, and had a higher service ceiling. The swept wings gave it better performance in the transonic regime where jet fighters increasingly operated. On November 8, 1950, the first jet versus jet combat in history occurred over North Korea. Lieutenant Russell Brown, flying an F-80, encountered a MiG-15 near the Yalu River. Brown's account of the engagement entered aviation history. I was flying top cover for a bombing mission when I spotted the MiG below me at about 20,000 feet. He didn't see me initially. I rolled inverted and dove, using the altitude advantage. The F-80 accelerated beautifully in the dive, faster than the MiG could manage. I came out of the dive about 1,000 feet behind him and slightly below. He started a climbing turn when he saw me, but I had speed advantage from the dive. I fired a 3-second burst with all 6 guns. I saw hits sparkle along his fuselage and wing route. The MiG rolled inverted and went straight down, trailing smoke. I didn't see the pilot eject. Brown had shot down the first jet aircraft destroyed by another jet in combat. The engagement demonstrated tactics that would become standard. The F-80, like Kelly Johnson's earlier P-47 Thunderbolt, was heavier and less manoeuvrable than its opponent, but could use energy tactics, diving attacks, and superior firepower to win engagements. Over the next months, F-80 pilots would destroy 37 MiG-15s in aerial combat. But the MiG's advantages were real. At high altitude, where most jet combat occurred, the swept-wing MiG could outmaneuver and outclimb the straight-wing F-80. American pilots were forced to rely on superior training, better tactics, and excellent gunnery to overcome the performance deficit. The 650 caliber machine guns, the same weapons that had devastated the Luftwaffe in the P-47, proved equally effective against jets. The F-80's guns were perfectly harmonized, creating a dense cone of fire that could tear apart an aircraft in seconds. Lieutenant Colonel Bruce Hinton, who shot down the second MiG-15 kill, described the effectiveness. When you got your sight on a MiG and pressed the trigger, those 6 guns just shredded them. The armour-piercing incendiary rounds would punch through aluminum skin and detonate inside, starting fires and destroying structure. I saw MiGs come apart in mid-air from a single good burst. The concentration of fire was incredible. By mid-1951, newer American fighters like the swept-wing F-86 Sabre were replacing the F-80 in air-to-air combat roles. The Sabre, which owed much to lessons learned from the P-80 program, was better suited to fighting MiG-15s at high altitude. But the F-80 continued flying combat missions in the ground attack role where its stability, reliability, and heavy gun armament made it highly effective. The final statistics from the Korean War showed F-80s had flown over 98,000 combat sorties, destroyed 37 enemy aircraft in aerial combat while losing 14 to MiGs, and proved that Kelly Johnson's design was as combat effective as it was innovative. German engineers who had dismissed American jet development capabilities had grossly miscalculated. The nation that had been years behind in 1943 had not only caught up but surpassed German achievements by 1945. This reversal occurred because American engineers understood something their German counterparts missed. The key to military aviation success wasn't producing the most technically advanced aircraft. It was producing effective aircraft that could be manufactured in quantity, maintained in field conditions, and flown by average pilots. The Me-262, for all its technical sophistication, was a maintenance nightmare that required extensive ground support and experienced pilots to operate safely. The P-80 could be maintained by mechanics with basic training and flown by pilots fresh from flight school. In military terms, that difference was decisive. Post-war analysis revealed the full extent of German miscalculation. While German engineers had focused on achieving maximum performance through complex designs, American engineers had focused on achieving adequate performance through simple, reliable designs that could be produced efficiently. Kelly Johnson's approach of using small teams with minimal bureaucracy, aggressive timelines, and direct communication between design and manufacturing represented a fundamental innovation in aircraft development. The Skunk Works model Johnson pioneered with the P-80 program became the template for rapid development of advanced aircraft. Over subsequent decades, the Skunk Works would produce the U-2 spy plane, the SR-71 Blackbird, and the F-117 stealth fighter, each representing revolutionary advances achieved through Johnson's methods. The Germans who had laughed at American jet projects in 1944 lived to see American jets dominate the skies of Korea, Vietnam, and beyond. They saw Kelly Johnson's simple, clean design approach triumph over their complex, sophisticated designs. They learned too late that mockery of your opponent's capabilities is poor strategy. In 1955, at an aviation conference in London, Kelly Johnson was invited to speak about the development of the P-80 Shooting Star. Among the audience were several former German aircraft designers who had immigrated to Britain and America after the war, including members of the team that had developed the Me-262. During the question and answer session, one of these engineers, whose name was not recorded in the conference proceedings, stood and asked a pointed question. "Mr. Johnson, your P-80 was undeniably successful, but it used a British engine design and straight wings. Our Me-262 had swept wings and German-designed engines. Doesn't this suggest that German engineering was still more advanced, even if American production methods were superior?" Johnson's response was characteristically blunt and became one of the most quoted exchanges in aviation history. "With respect, sir, you're confusing complexity with advancement. Yes, the Me-262 had swept wings. They were necessary because your engines were mounted on the wings, creating aerodynamic problems that sweep helped solve. We mounted our engine in the fuselage, eliminating the problem entirely. Your aircraft required swept wings, ours didn't. As for engines, we used the Halford because it was reliable and available. Could we have designed our own? Certainly. But that would have taken time we didn't want to waste. Engineering isn't about proving how clever you are. It's about solving problems efficiently. You built an aircraft that required 1,500 hours of maintenance for every hour of flight. We built one that required 50 hours. You built an aircraft that killed more German pilots in accidents than we shot down in the first months of combat. We built one that pilots could fly safely after minimal training. So yes, your engineering was more complex, but ours was more advanced because advancement means accomplishing the mission with the minimum necessary complexity." The room was silent. Johnson continued, his voice softer but no less direct. "The Germans didn't lose the jet race because you lacked brilliant engineers. You had some of the finest aeronautical minds in the world. You lost because you were trying to win a technical competition while we were trying to win a war. Those require very different approaches to engineering. This exchange crystallized the fundamental difference between German and American approaches to military aviation during World War II and beyond. German engineers, operating in a culture that valued technical sophistication and theoretical perfection, created aircraft that were engineering marvels but operational nightmares. American engineers, operating in a culture that valued pragmatism and efficiency, created aircraft that were mechanically simpler but militarily superior. The Me-262, Germany's jet fighter that had seemed so advanced in 1944, required exotic alloys for its turbine blades because German metallurgy couldn't produce the heat-resistant materials needed for reliable engines. The engines had to be completely rebuilt after 10 hours of operation. The aircraft suffered from compressor stalls during rapid throttle movements, often causing engine fires. Landing gear frequently collapsed due to the aircraft's high landing speed and poor weight distribution. Pilots needed extensive training to operate the aircraft safely, training time that Germany couldn't afford in the desperate final years of the war. The P-80, by contrast, used conventional aluminum alloys throughout most of its structure. The Allison J-33 engine, refined from Frank Whittle's original design, could operate for 180 hours between overhauls. Throttle response was smooth and predictable. Landing characteristics were benign enough that pilots transitioning from propeller fighters adapted quickly. A fresh flight school graduate could be combat ready in an F-80 within weeks. A German pilot needed months to master the Me-262, time that Germany didn't have. These differences extended beyond the aircraft themselves to the entire support infrastructure. The Me-262 required specialized ground equipment, trained technicians familiar with jet engines, and extensive facilities for maintenance. Forward deployment was extremely difficult. The P-80 could be maintained with relatively simple tools by mechanics who understood basic principles. It could operate from austere airfields with minimal support equipment. German engineer Hans Multhop, who had worked on swept wing research during the war and later immigrated to America, wrote extensively about these differences in the 1960s. His memoir, published shortly before his death, included a chapter titled "Why We Lost the Technical War" that was remarkably candid about German failures. We were so proud of our swept wings, our sophisticated engines, our advanced weapon systems. We convinced ourselves that technical superiority would overcome material disadvantages. What we failed to understand was that technical sophistication is worthless if it prevents you from fielding effective weapons in useful numbers. The Americans understood this instinctively. They weren't trying to build the perfect aircraft. They were trying to build good enough aircraft that could be produced by the thousands and flown by average pilots. That's why they won. Not because their engineers were better than ours, but because their engineering philosophy was better suited to industrial warfare. The P-80 program also revealed something else that German engineers had failed to anticipate: American organizational innovation. Kelly Johnson's Skunk works represented a revolutionary approach to aircraft development that completely bypassed the bureaucratic inefficiencies that plagued both German and conventional American programs. By creating small teams with direct authority, minimal reporting requirements, and freedom from interference, Johnson achieved development speeds that seemed impossible under traditional methods. The German aircraft industry, despite its technical sophistication, was hobbled by bureaucratic infighting, interference from Nazi Party officials who understood nothing about aviation, and a requirement to constantly justify decisions to multiple oversight organizations. Hermann Göring's Luftwaffe procurement system was particularly dysfunctional, with competing agencies often working on duplicate programs while critical projects languished for lack of resources. Willy Messerschmitt, designer of the Me-262, spent as much time navigating political battles with Ernst Heinkel and Kurt Tank, his rivals in the German aircraft industry, as he did actually designing aircraft. Resources were allocated based on political connections rather than technical merit. Hitler personally interfered with aircraft development, demanding modifications that delayed programs by months. The entire system was designed to prevent any individual or organization from accumulating too much power, which had the side effect of preventing anyone from making decisions quickly. Kelly Johnson operated in an environment that was almost the opposite. General Arnold gave him a clear objective and complete authority to achieve it. Lockheed management supported the Skunk works, but didn't interfere with its operations. The small team meant Johnson could make decisions in minutes that would have required weeks of committee meetings in a conventional organization. When problems arose, they were solved immediately rather than being studied, reported on, and eventually addressed through proper channels. This organizational advantage was as important as any technical innovation. The P-80 succeeded not just because it was well designed, but because the process that created it was optimized for rapid development. German engineers, no matter how brilliant, couldn't overcome the dysfunction of the system they worked within. The intelligence failure that led Germans to underestimate American jet development was itself symptomatic of deeper problems. German technical intelligence during World War II was surprisingly poor for a nation that prided itself on scientific rigor. The intelligence services were fragmented, with military intelligence, party intelligence, and industrial intelligence all operating independently and often withholding information from each other. Reports on American aviation developments were often dismissed if they contradicted existing assumptions. When intelligence indicated that American bomber production exceeded German estimates by factors of 2 or 3, the reports were rejected as obviously false. When information suggested American fighters were becoming competitive with German designs, it was attributed to propaganda. The possibility that American industry could match German technical innovation while maintaining massive production volume was simply not accepted. This willful blindness extended to the highest levels. Albert Speer, Minister of Armaments and War Production, wrote in his memoirs about presenting production statistics to Hitler that showed American output exceeding German production by ratios of 5 to 1 or greater in some categories. Hitler refused to believe the numbers, insisting they must be falsified. When Speer insisted the intelligence was reliable, Hitler declared that it didn't matter because German weapons were qualitatively superior. This focus on quality over quantity became a self-justifying delusion. Every German technical advantage, whether real or imagined, was cited as proof that German engineering could overcome material disadvantages. The swept-wing research that led to the Me-262's wing design was held up as evidence of German superiority, even as Me-262s sat grounded for lack of fuel, while American straight-wing fighters ruled the skies. The reality, understood too late by German engineers, was that quality and quantity were not opposed but complementary. American industry achieved both. The P-80 was qualitatively excellent and produced in quantity. The P-51 Mustang was arguably the best piston engine fighter of the war and built by the thousands. The B-29 Superfortress was the most advanced bomber ever created and rolled off production lines by the hundreds. German engineers after the war often attributed American success to unlimited resources, as if resources alone could produce advanced aircraft. This interpretation missed the point. America had resources, but so did the Soviet Union, and Soviet aircraft, while effective, never achieved the refinement of American designs. Resources enabled American success, but the success itself came from organizational methods, engineering philosophy, and industrial processes that turned those resources into effective military power. The P-80 Shooting Star served with the US Air Force until 1959, a remarkable 14-year operational lifespan for a first-generation jet fighter. Even after being replaced by more advanced fighters in frontline service, P-80s continued flying as advanced trainers. The T-33 variant, essentially a two-seat trainer version of the P-80, served even longer, with some air forces operating T-33s into the 21st century. This longevity testified to the fundamental soundness of Kelly Johnson's design. Unlike the Me-262, which was obsolete within months of entering service due to its operational limitations, the P-80 proved adaptable and reliable enough to remain useful for decades. When more advanced fighters like the F-86 Sabre appeared, they incorporated lessons learned from the P-80 program rather than representing completely new approaches. The legacy of the P-80 extended far beyond the aircraft itself. The Skunk Works methodology that Johnson pioneered became the model for rapid development of advanced technology. The U-2 spy plane, developed in the 1950s using Skunk Works methods, went from contract to first flight in 8 months. The SR-71 Blackbird, one of the most advanced aircraft ever built, was developed in similar secrecy with similar efficiency. The F-117 stealth fighter, which revolutionized air combat in the 1991 Gulf War, emerged from the same organizational approach. These programs succeeded because they followed Kelly Johnson's principles: small teams, minimal bureaucracy, direct communication, and freedom from interference. The methods that produced the P-80 in 143 days proved applicable to increasingly complex projects, suggesting that the real innovation wasn't the aircraft but the process that created it. Modern aircraft development, ironically, has often abandoned these principles. Current fighter programs frequently take decades from concept to operational service, cost hundreds of billions of dollars, and involve massive organizations with layers of oversight. The F-35 Joint Strike Fighter, for example, has been in development since 1992 and still faces operational limitations. Its per-unit cost exceeds $100 million, and its development has involved coordination between multiple military services, allied nations, and hundreds of contractors. Kelly Johnson, who died in 1990, lived to see modern acquisition systems producing results he found incomprehensible. In one of his last interviews, discussing the F-35 program then in its early stages, Johnson was characteristically blunt. "We built the PT in less than 5 months with 23 engineers and 105 shop workers, for a total program cost of $600,000. It worked the first time we flew it, went into combat, and served for 14 years. Now you're telling me this new fighter will take 20 years to develop, cost more than the entire World War II aviation budget adjusted for inflation, and involve thousands of engineers. Something has gone very wrong with how we develop aircraft. The bureaucracy we bypassed in 1944 has returned with a vengeance." Whether Johnson's critique was fair is debatable. Modern fighters are incomparably more complex than the P-80, integrating stealth technology, advanced sensors, network connectivity, and weapon systems that didn't exist in Johnson's era. But his fundamental point remains valid. At some point, complexity and oversight become counterproductive, slowing development to the point where aircraft are obsolete before they enter service. The German engineers who laughed at American jet projects in 1944 learned a hard lesson about underestimating opponents. But there's a broader lesson in the P-80 story about how innovation actually occurs. Technical sophistication alone doesn't guarantee success. Organizational efficiency, clear objectives, and freedom to experiment are equally important. The best engineering happens when talented people are given difficult problems, adequate resources, and freedom from interference. Germany in World War II had talented engineers but hobbled them with dysfunction, interference, and a dysfunctional procurement system. America, through the Skunk Works program, QWORKS, discovered that removing obstacles was as important as providing resources. The P-80 succeeded not just because Kelly Johnson was brilliant, but because he was allowed to be brilliant without interference. In 1983, at a symposium marking the 40th anniversary of jet aviation, surviving members of Kelly Johnson's original P-80 team gathered with German engineers who had worked on the Me-262. The event, held at the Smithsonian Air and Space Museum, was intended to celebrate jet aviation's pioneers from both nations. A restored P-80 and Me-262 sat side by side in the museum's main hall. During a panel discussion, one of the German engineers, now in his 80s, made a remarkably frank admission. We convinced ourselves that technical sophistication equaled superiority. The swept wings, the complex engines, the advanced weapons, these were proof of German engineering excellence. What we failed to understand was that military aviation isn't about building impressive machines. It's about building machines that accomplish military objectives. Your P-80 accomplished those objectives better than our Me-262, not because it was more sophisticated, but because it was more practical. We were engineering for theoretical perfection. You were engineering for operational effectiveness. That's why we lost. Art Vierek, one of Johnson's original engineers on the P-80 project, responded with equal candour. We had one advantage you didn't. We could see your mistakes and learn from them. The Me-262 taught us what not to do. Make it too complex and it won't work in field conditions. Make it too demanding and average pilots can't fly it. Make it too difficult to maintain and it won't be available when needed. So we did the opposite. We made it simple, easy to fly, and reliable. Not because we were smarter, but because we learned from your experience. This exchange captured something important about technological development. Innovation rarely happens in isolation. The P-80 was not created in a vacuum, but emerged from careful study of British jet technology, German jet fighters, and American production methods. Kelly Johnson's genius was not in inventing entirely new concepts, but in synthesizing existing knowledge into an optimized design. The Germans, operating from a position of early advantage, fell into the trap of believing their initial lead was permanent. They assumed American engineers, lacking experience with jets, would take years to catch up. This assumption ignored American strengths in industrial engineering, production efficiency, and organizational innovation. It also ignored American willingness to learn from others, rather than insisting on indigenous development of every technology. The Allison J33 engine that powered the P-80 was based on Frank Whittle's British design, licensed and improved by American engineers. There was no shame in this. The British had pioneered jet engines, and using their work as a foundation allowed American engineers to skip years of basics, research, and move directly to refinement and optimization. German engineers, proud of their indigenous engine designs, spent precious time solving problems the British had already addressed. This willingness to adopt and improve foreign technology, rather than insisting on purely domestic development, gave American programs flexibility that German programs lacked. When better approaches emerged, American engineers could incorporate them immediately. German engineers, operating in a system that valued autarky and German exceptionalism, were pressured to develop German solutions even when superior foreign technologies existed. The P-80 story also illustrates the danger of extrapolating from current performance to future capability. German engineers in 1943 and 1944, observing the pathetic 59-era comet, concluded that American jet development was hopelessly behind. This was true at that moment, but they failed to account for American industrial learning curves, which were remarkably steep. American industry had demonstrated repeatedly that initial failures were quickly overcome through iterative improvement and massive resource application. The Liberty engine of World War I was initially problematic but improved rapidly to become one of the war's best aircraft engines. The B-29 Superfortress was a maintenance nightmare in early service, but was refined into a highly reliable bomber within months. American industry's ability to identify problems and implement solutions at scale was unmatched. German engineers, operating in an economy that was resource-constrained and industrially overstretched, couldn't imagine the speed with which American industry could iterate and improve. By 1950, when F-80 Shooting Stars faced MiG-15s over Korea, the aircraft that German engineers had never expected to see was engaging in combat against fighters designed with captured German swept-wing research. The irony was profound. German swept-wing research, conducted during World War II, had been captured by the Soviets and Americans. The Soviets used it to develop the MiG-15. The Americans used it to develop the F-86 Sabre. German innovation had been absorbed and improved by both sides. The F-80, with its straight wings and conventional design, held its own against the swept-wing MiG-15 until swept-wing American fighters arrived. This validated Kelly Johnson's approach. The straight wing was simpler to manufacture and adequate for the mission. When swept wings became necessary for performance reasons, American industry adopted them. But they didn't start with complexity they didn't need. In the decades after World War II, captured German engineers contributed significantly to American and Soviet aviation programs. Wernher von Braun became famous for his work on American rockets and the Apollo program. Less well-known German engineers worked on aircraft development, bringing their expertise in high-speed aerodynamics, jet propulsion, and advanced materials. But they worked within American organizational structures that emphasized results over theoretical elegance. Many of these engineers, in memoirs and interviews, expressed frustration with German wartime programs and appreciation for American methods. Hans von Ohain, who had developed Germany's first jet engine in parallel with Frank Whittle, worked for the US Air Force after the war. In a 1978 interview, he reflected on the differences between German and American approaches. In Germany, we were always trying to achieve perfection. Every design had to be theoretically optimal, even if this made it difficult to manufacture or maintain. In America, I learned that good enough, delivered on time, beats perfect, delivered late. The P-80 program exemplified this. It wasn't the perfect jet fighter, but it was good enough, and it was available when needed. That made it better than the perfect fighter that arrives too late. This philosophy, pragmatic and results-oriented, characterized American engineering during and after World War II. It wasn't about settling for mediocrity. American engineers pursued excellence, but they defined excellence as solving problems effectively rather than achieving theoretical perfection. The P-80 was an excellent aircraft not because it pushed every technological boundary, but because it balanced performance, reliability, manufacturability, and ease of operation in ways that made it militarily effective. The final irony of the P-80 story is that the aircraft almost didn't happen. If General Arnold had accepted the conventional wisdom that jet development required years of careful work, if he hadn't been willing to gamble on Kelly Johnson's unorthodox approach, if Lockheed management had insisted on following normal procedures, the P-80 would never have been built in 143 days. It would have been developed conventionally, taken years to complete, and arrived too late to demonstrate American jet capabilities before war's end. Arnold's willingness to bypass normal procedures, Johnson's confidence that rapid development was possible, and Lockheed's support of the Skunk Works approach created conditions for success. These factors, organizational and cultural rather than technical, were as important as any engineering decision. The P-80 succeeded because the system that created it was optimized for success. German engineers laughed at American jet projects because they evaluated American efforts using German assumptions about development timelines and technical approaches. They assumed American programs would follow the same tortuous path German programs had followed, with years of development, countless setbacks, and eventual deployment of complex aircraft that only expert pilots could fly. They couldn't imagine that American engineers would take a completely different approach, bypassing complexity in favor of simplicity, accepting British engine technology rather than insisting on indigenous development and creating an organizational structure specifically designed to eliminate obstacles. When the P-80 appeared, designed and built in less than 5 months, German engineers who learned about it refused to believe the timeline. It was impossible by German standards. But it happened because American standards were different. The laughter stopped when German test pilots flew captured P-80s after the war and realized the aircraft they had dismissed was superior to their own jets in most operationally relevant ways. In the end, the story of the P-80 Shooting Star is not primarily about technology. It's about how different approaches to engineering and organizational structure produce different outcomes. German engineers, brilliant and innovative, created technical marvels that were operationally limited. American engineers, equally capable, created practical weapons that achieved military objectives. Both approaches required expertise and dedication, but only one approach was optimized for winning a war. The Germans who laughed at American jet projects in 1944 learned too late that innovation isn't about who develops technology first. It's about who develops it most effectively. The MiS-262 flew before the P-80, but the P-80 succeeded where the MiS-262 failed because success in military aviation requires more than technical sophistication. It requires reliability, maintainability, ease of operation, and production efficiency. German engineers understood the first requirement, but neglected the others. American engineers understood that all requirements were equally important. Today, the P-80 Shooting Star is remembered as America's first successful jet fighter, and the aircraft that proved American industry could match any nation in developing advanced aviation technology. But perhaps its more important legacy is organizational. The Skunk Works methodology that created the P-80 demonstrated that small teams with clear objectives and freedom from interference could achieve extraordinary results. This lesson, learned over 143 days in a circus tent in Burbank, California, remains relevant for anyone attempting to develop advanced technology under time pressure. The German engineers stopped laughing when they understood what the P-80 represented. Not just a successful aircraft, but proof that American engineering, freed from bureaucratic constraints and focused on practical objectives, could produce results that matched or exceeded anything German technical sophistication could achieve. The jet age belonged not to the nation that pioneered the technology, but to the nation that could field effective jet fighters in operationally relevant numbers. That nation was America, and the P-80 Shooting Star was the aircraft that proved it.